When we look up at the night sky, it feels permanent, a quiet, unchanging canvas. But on February the 24th, 2026, in the mountains of northern Chile, that permanence failed, because astronomers started noticing subtle differences across the sky, one after another. In total, 800,000 in a single night, roughly 9 every second all night long. The reason we were suddenly able to notice that isn't that the universe changed overnight, but thanks to the Vera C Rubin Observatory. And in a single night it began flagging anything that didn't match what it had seen before. Asteroids drifting through star fields, new supernovae beginning to flare, distant galaxies flickering as black holes fed. So come with me, I'm the Cosmic Skipper, as we take a look at the telescope that woke up the sky. Rubin shatters the illusion that the night sky is still, a static canvas. It exists to detect change and flag it fast. And 800,000 alerts in a single night doesn't mean headline-making discoveries. It means 800,000 places where Rubin noticed something different. Rubin takes a fresh image and compares it to a reference template built from previous images of the same patch of sky. Then it subtracts the two, and whatever remains is the difference. Each of those changes triggers an alert within about 2 minutes of image capture. On that first night, the system worked exactly as intended, a reference subtraction from a 30-second exposure, and the first wave of alerts went out into the world. So what kind of machine can do this hundreds of thousands of times in a night? Rubin is built around one idea: cover a huge area of sky quickly and keep coming back. At its heart is the 8.4-meter Simonier survey telescope on Cerro Pachon, Chile. Mounted to it is the LSST cam, the largest digital camera ever built for astronomy. 3.2 gigapixels, a 9.6 square degree field of view, and 6 optical filters. During nighttime observations, roughly every 40 seconds or so, Rubin moves on, capturing, processing and comparing, so the what changed question gets answered at scale. This is all in service of the legacy survey of space and time, a 10-year time-lapse of the southern sky. Rubin is designed to take about 1,000 images a night, enough to cover the visible southern sky every 3 to 4 nights. And because the alert stream is near real-time and public, other observatories on the ground and in space can react quickly, coordinating follow-up while an event like a supernova is still unfolding. And that combination, wide coverage, constant revisits, instant alerts, means we can finally catch events as they begin. Too often in astronomy you hear about a fleeting event after the best moment has already passed. Rubin flips that by raising its hand while the event is happening. So what does Rubin actually catch in all of this? First, anything that moves. Asteroids, comets, distant objects beyond Neptune. Rubin's alerts help track solar system objects faster, tighten their orbits and flag anything worth a closer look, even out in the dim edges where theories like Planet 9 live. Second, supernovae. Rubin can catch the earliest flicker, the first rise, so that other telescopes can pivot and watch the explosion unfold in real time. And third, the weird stuff. Active galaxies that flare, stars that dim, sudden one-off transients that don't fit neat categories yet. Rubin's alerts don't just find what we already know how to name, they'll find things we haven't learned to ask for. So if you take one idea about Rubin, let it be this. Rubin isn't taking a still photograph of the universe, it's imaging a living system. And on February the 24th, 2026, it finally watched that living system change in real time. 800,000 pings on night 1 with millions more to come. And somewhere in that flood of data between the familiar flicker of a variable star and the bright flash of a dying sun, there will be surprises we haven't even named yet. That's the promise of Rubin. Not that it will show us the universe, but that it will reveal a dynamic universe we haven't been able to see clearly until now.